Now, in this session, I think I've solved the problem of memory requirements. I've invented a technique that ensures that I have enough memory, so I don't think that will be a problem again, unlike the previous mini sessions. I've also learned to move the tripod closer to the screen, even though the bed's in the way, so I moved the bed a little, but it's a tripod with adjustable length legs. So the front leg I made a lot shorter and rested on the bed. So if only I'd thought of it earlier. So you may notice now that the screen is taking up more of the image, a higher percentage of the image, in fact nearly all of it. And so hopefully the writing will be a little larger. But I'm still thinking seriously of asking the same company that made me this whiteboard to make me another one, which would go from about this height. Well, I don't know if we can't even see it, I think, but like say 10 centimeters taller, and maybe even a meter longer. So a really big board. Because I just need it. Well, I know I will need it when I get onto the graduate level physics and math, especially on physics. There are just so many equations, long equations with many terms, and I'll just need a big board. Right. Well, let's start. Now, from the previous session, quite a bit of algebra, quite a bit of math. Found a technique to calculate the energy of the single bound state in the delta well. Now, remember a delta well looks a bit like a delta function. A delta function is just basically like a spike. It's a spike. So effectively infinitely thin, infinitely tall, yet the area under that curve is finite, usually 1. For a direct delta function, that area is usually 1. Okay, so now in this session, we will find an alternative technique for calculating the energy of the eigenvalue of the STI, the Schrödinger time-independent equation, and it's in some ways easier and very convenient for later. Now, by later, when this lecture is finished, I will then jump in the textbook to one of the appendices. It's Appendix A, I think. It's on page 145 of your text, if you're following this closely. So the appendix title is called "The One-Dimensional Infinite Array of Delta Wells." And this particular model was invented by Kronig and Penny, so it's called the Kronig and Penny model. So you can see that. Now this appendix, Appendix A, is 1, 3, 5, 6. It's 6 pages, so it's pretty well almost a short chapter in its own right. But it's important because it derives results, the so-called conduction bands. And so what? Well, those conduction bands are critical to the behavior of transistors. So if you really want to know how a transistor works, all this stuff becomes the quantum mechanics behind the functioning of the transistor. And if you think about it, the transistor is probably one of, if not arguably, the greatest invention of the 20th century, right? Because due to the transistor, we have our modern electronic information age that's just changing everything, changing our politics even, right? Due to the internet and openness and greater freedom of speech and pressure on dictatorships and all that stuff. So, important stuff. So I'll do that appendix, and that'll be after this lecture. So lecture 3 will not be followed immediately by lecture 4. It will inserted will be this appendix on effectively an infinite array of delta worlds. Now, in this session, we will begin, because I've again run out of board, we will handle the quantum mechanics of 3 delta worlds. So, of course, we'll use the analysis and this technique, this new technique we'll do today, for analysing the case of 3 delta worlds. All right. So, and this technique is it's better for analysing when you have a periodic array of spike worlds or delta worlds. Right? Okay, so here's the essential idea. We're going to we'll use the usual the usual constraints on the eigenfunction, the wave function. Has to be single valued. It has to be normalizable, and it has to have continuity in terms of the value itself, you know, your u at some sort of boundary, and the differential, you know, the gradient has to be the same. You have to have continuity gradient on either side of the boundary. So in this second technique for finding the energy of the wave function, the eigenvalue, we will use continuity of the gradient, right? So here's the idea. It's probably easy just to think of it visually. Here's your boundary. Like in this region 2, your potential is 0. Okay, and in region 1 and region 3 here, your potential is V0. Right? Your V0 is finite, but grows and grows effectively to infinity. So at the same time, the width here, which would be 2a, or of the order a, so this width here gets very, very narrow, right? So the V0 gets very large, and the a gets very, very thin, such that the product, you remember from previous session, the delta, we defined it, that's the product of the width times the depth. So a times V0. So delta is a times V0. The width times the depth or the height. Okay. Now, so before your a here gets too small, so you can see it, visualize it. We want continuity of the gradient of the 2 sets of curves. Now we've got the wave function u in the region 2 where the potential is 0. So you know, just draw that this way. Now let's assume. Now the potential is symmetric, right? The potential is sort of a mirror image, and therefore from that very useful theorem that we did a couple of sessions back, if the potential is symmetric, then the wave function has to have odd or even parity. That was a theorem that we did, and it's saving us a huge amount of work. A wonderful result, right? A great work saver. So we'll only analyze, you know, say we only have to solve half the problem, and then we know what the other half is, you know, for the wave function, just by symmetry or anti-symmetry. In other words, parity is even or parity is odd. So the wave function is either an even function or an odd function. Right? So we only have to solve half the problems. So, yeah, great work saver. All right. So so in this case, for this second method, we will use the continuity of the gradient. So in other words, let's say on the right hand side here, so on the barrier between region 2 and 3, the gradient of this wave function here, you know, infinitely close to the barrier here, on the left side though, that gradient here has to be equal to the gradient of the wave function in region 3. So as you get infinitely close on the right hand side to this barrier between areas or regions 2 and 3, that gradient there has to be equal to that gradient there. Okay? That's continuity of gradient. Now a similar story here on the other side. So the gradient, so here's your wave function u in region 2, where the potential is 0, v is 0. Okay? So that gradient there has to be equal to this gradient here. Now this gradient here you calculate using the wave function u in region 2. And this gradient, this one here, that you calculate using the wave function in region 1. Okay? And at that point, just there, right on the boundary, those two gradients have to be equal to each other. And these two gradients, at that point, have to be equal to each other. Continuity of the gradient. Right? Now, given that, given the symmetry and so forth, so what we're going to do now is talk about the difference between the two gradients. Now, not this one and this one. There's no difference, right? And there's no difference between that one and that one. But there is a difference. I mean, you just see it visually. There is a difference between this gradient and this gradient, right? This gradient's sort of this way, and this gradient's that way. Okay? So we will find an expression for the difference in the gradients. In fact, it works out, it's the right-hand gradient minus the left-hand gradient. So here, like, so what is the gradient? Well, if you've got your wave function u here and here and here, so you've got, in a sense, three wave functions, but they meet up here, and the gradient's the same that way and the same that way. So, so this gradient here would be du by dx on the right-hand side, right? Du by dx on the right-hand side, and the gradient here would be du by dx on the left-hand side. And the difference, because that's what's important in this this session, is it's the difference in the gradients that we're going to use. This difference will be useful later. Well, in two cases, for solving the 3 delta well problem, and the techniques that we'll learn from solving that, and we won't be able to finish it this session because I've run out of board, but we can start. The techniques that we learn from solving the 3 delta well problem, then we can carry over for solving the infinite number of spikes, infinite number of delta wells. And we can use that analysis to analyze the behavior of electrons in periodic arrays of, like in silicon, for example.